Hi, welcome and happy International Earth Day to you all. That's today. Today is all about Earth, the planet we live on. Now, we're going to talk all about this bit of rock flying around the sun we call home. It's in partnership with the Parks Trust and their amazing Nature Day. Now, our planet is a biological spaceship, perfectly created for life of all sorts of shapes and sizes to survive as we fly in orbit around this huge ball of piping hot plasma in inhospitable space. That sounds kind of terrifying. Without the planet, we would be fried, frozen and suffocated kind of all at once. So let's take a look at how this amazing planet came to be, and by the end of this talk I hope it will you'll have a more of a sort of appreciation for our planet Earth. But the Earth wasn't always the way it is today. 4.6 billion years ago there was a gravitational collapse in a huge molecular cloud, which is part of a nebula, which spun slowly over time into a flattened disk of swirling dust and gas and elements, with the sun eventually igniting in its middle and kind of blowing all the dust and that away. Now, our planet formed in this disk as dust and grains started to sort of stick together and clump, forming slowly larger and larger and larger, what was known as meteoroids, eventually leading to an asteroid-sized planetesimal, is what they call it now, which became large enough to sweep up all the rest of the stuff around it, all the gas and other meteoroids and stuff like that all around it, into its orbit, clumping it all together. So the gravity of this planetesimal helped pull the heavier elements to its centre, slowly creating the layers we know today in the Earth. Now, Earth then endured some large-scale impacts. There was loads of impacts throughout its young life, as you can imagine. It's flying around in orbit, picking up all these bits of rocks, things that are, other planetesimals that are quite bigger than it. So one of these big sort of large-scale impacts was a planetesimal called Theia, which, if you've listened to our moon talk, which is on our YouTube channel if you want to have a look, it actually created our moon in a shower of debris that went all around the planet and sort of clumped together, making the moon. Now, both of these planets kind of merged together, us and Theia. I think they say most of Theia got thrown out in the debris, some fell back down to Earth, some created the moon. So it clumped together in orbit around us, the moon. These impacts are believed to have changed Earth's alignment, or what's known as its tilt, because we're not perfectly sort of 90 degrees, we're at a sort of angles, so we're tilted away, which is why we get the seasons, depending on, whether we're facing towards or away from the sun. You get summer and winter, especially in the northern hemisphere where it changes quite a lot. So that's the tilt of the Earth. But again, that hasn't always been the same tilt it is today. It does change slightly around every 41,000 years, so it's quite a long time. But it does change by a couple of degrees back and forth, and we would believe that it would actually move a lot more, and sort of like as it spins it would sort of wobble more as it goes around in orbit, if it wasn't for our moon, which actually kind of helps stabilize it, keeping the seasons pretty mild. Otherwise we would have some probably extreme seasons every 41,000 years as it tilts back and forth. Now, as more impacts hit us, adding to and heating up the planet, the pressure in the core kind of grows. Volcanic activity begins as a crust sort of forms on the edge. This is formed by sort of like outgassing. All the gas goes up, kind of cools and creates this crust around it. Possibly ice deposits as well from comet impacts that came flying down, maybe bringing us a bit of water, H2O and bits and bobs, other elements. Eventually creates its kind of Earth's first sort of inhospitable atmosphere. I believe it's kind of like mostly carbon dioxide, maybe some nitrogen. Earth has had quite a few different atmospheres as time has gone on, and we'll talk about maybe one or two other ones of them, but mostly unbreathable at this time. Just as this all kind of happens, Earth then experiences what's known as the late heavy bombardment, which wasn't really late for us because we went around, it was quite before, but it was later on. Something happened and all these, I think it was Jupiter, but kind of sweeping in towards the sun a bit more and then getting dragged back out. And while it did this, it threw loads of bits of rock at us, probably from asteroid belt that's in between Mars and Jupiter. Maybe that's why another planet that was meant to be there didn't clump together, because a lot of this stuff got thrown towards us. So the late heavy bombardment, they reckon, kind of released extra water, all came down. The Earth actually released more water as well from its mantle, and it eventually becomes covered in an ocean. So it's actually suggested that around this time, once there was an ocean everywhere, so Earth wasn't actually just Earth, it was pretty much an ocean. They reckon that this is when primitive life then appeared in the growing sea. It was in the form of sort of blue-green algae, so not very exciting stuff. But you can imagine these huge seas with these big plumes of blue and green algae all over the surface. Then after this, its first supercontinent, called Volbara, is what I'm going to call it, grew, which would eventually kind of break up and slowly form all the continents we know today. There will be a lot of moving about of it really, really slowly with tectonic plates and things like that. So the now named Earth was actually started as pretty much sea, and today it is still around about 70% ocean. So I always say that we actually call it Earth, and really we should probably call it sea. It's probably just that we're biased because we generally live on the Earth, so we're going to call it Earth, aren't we? Now the Earth's atmosphere then evolved into one that was oxygen rich due to all this bacterial photosynthesis was going on, and that was pumping out unwanted oxygen, which is highly volatile and a poisonous gas to them and other organisms, so they didn't want to keep that within them, so they kind of pumped it out. Some of them locked it into the ground and stuff, and rocks and things like that, which unknowingly to them started to create the first of 5 mass extinctions of life. The oxygen went really high, all the other bacteria and stuff, they couldn't actually survive this high oxygen, and it also plunged the Earth's temperature due to the gases released doing the opposite to global warming. So carbon dioxide helped keeps it warm. It then all kind of turned to methane and oxygen in a way, I think. I'm not a chemist, so don't judge me on that one. And so all the heat sort of kind of went back out into space. So we had a global cooling effect that killed off a lot of the early life. So we're lucky to be here, really. And this is the one of 5. And that's just mass ones. But again, life, it evolves. So it soon evolved to deal with oxygen. And we can see today it's helped create a complex life like us, with respiration. So we breathe in oxygen and we use oxygen and we survive, whereas plants do the opposite. So we're very lucky that we managed to survive this and use oxygen to our advantage. So from tiny bacteria to giant dinosaurs, some life died out, others evolved, and the creatures that seem sort of best suited to be able to evolve to Earth's changing climates and times, funnily enough, insects. So not us, not lizards, not crocodiles, although crocodiles are pretty hardy. They've been around for millions of years when the dinosaurs were around as well. So insects. Now 300 million years ago, our atmosphere, as you know, had a higher oxygen level, which helped insects grow into huge beasts. There was a dragonfly with a 28-inch wingspan, or a 9-foot millipede. Not the sort of place you're probably going to want to live nowadays. I mean, people get scared of spiders the size of their hands, so imagine a millipede 9 foot long. That's pretty scary. Luckily they're all extinct now. I say luckily, it's quite sad. I would like to see it. I like bugs. Now today's insects are small, which a lot of people probably have a sigh of relief for. But what they lack in size, they make up for in numbers. So size doesn't always matter. There are approximately 1.4 billion insects for every person on Earth. That's quite a lot. And the total weight of all the insects together on the planet, and a lot of them we haven't actually discovered yet, we've still got loads more to discover, they say is around 70 times more than the population alive today. So the total weight is 70 times more than us. So let's not upset the insects, let's let them be. But they seem to be the ones that seem to be able to survive all these climate changes, all the mass extinctions. They seem to do really well. It might be because they're small, they don't really need to eat a lot, live underground, so they're protected quite a lot of the time. Or maybe it's their kind of hive nature and how it works. Who knows? But we like to think we own the planet, but no, really, it's owned by insects. So next time you see an insect crawling around, don't stamp on it. Give it a bit of respect. It's evolved for millions of years. Now, we all know there were dinosaurs on the planet, and we love dinosaurs. Big, crazy sort of reptiles running around, eating each other and stuff. Unfortunately, they did die out. And they died out, they think, because of an asteroid that kind of crashed into the Earth, and there's other things that might have affected it as well. The insects still survived and thrived, but with the dinosaurs all being sort of annihilated and taken out, there was like this niche now. There was a gap in sort of the habitat for where you could go, and this gave mammals the chance and the room they needed to evolve, and slowly over time stand on 2 feet and grow into the hairless apes you see driving, eating and talking to each other today. No looking at your partners or your mums and dads. Right, back to our planet. Our planet has an atmosphere. We've just spoken about that. The atmosphere we have today is very nice for us. Was it oxygen, nitrogen, a bit of carbon dioxide, other bits and bobs in there, probably a lot of pollution now as well. But has an atmosphere, and along with the atmosphere and our magnetic field, it protects us from all the dangers of space. It has different layers, starting from the part we know and breathe up to. So from where we are to about the height of maybe Mount Everest, that's the bit of we know and that we enjoy and that we can fly around in. You then got the troposphere, and that's from 6 to 10 miles high and covers about 75 to 80% of our entire atmosphere. Is there. Most of the weight of our atmosphere is there. You'll find most types of clouds and almost all the weather occurs within this layer, including the jet streams, which we'll talk about a little bit later. Jet streams are quite important of how weather moves around and stuff. The next layer of our atmosphere is the stratosphere, where you can find the protecting ozone layer that protects us from all those harmful rays from the sun, as we know, because we started to destroy it. I think it was back in the sort of 80s, 90s. Luckily it started growing back now. We've been looking after it, stopped using the harmful gases which destroyed it. So the stratosphere is between 20 to 30 miles and looks after us. You then got the mesosphere, and this is where weather balloons and other aircraft can't fly high enough to reach, so we don't really know that much about it. It is the place where meteors, when you see them burning up in the sky, this is kind of where they vaporize. That is known to create a phenomenon known as noctilucent clouds, which is all these sort of crystals from the vapor that they've done, all frozen up in the atmosphere. And when the light sort of hits it from the bottom, when the sun's either rising or setting, about 45 minutes either side, you could sometimes see these noctilucent clouds, which are cool, and this is where they sit. And that's at around 30 to 50 miles. Then you've got the thermosphere. Although considered part of Earth's atmosphere, the air density is so low in this layer that the most common definition says that space actually begins at an altitude of about 62 miles. I believe the thermosphere goes a lot higher than that. And this is where the International Space Station orbits the Earth. And it's within the thermosphere. So when you see it flying past there, it's actually kind of still within Earth's atmosphere, even though it's that high up. But that depends on where you decide, space begins. 62 miles up, apparently. Now, we did mention jet streams. They do play a part in Earth's weather, as does the planet's spin, its core temperature, and the sun. So, let's say if you live in one place your entire life, you'll soon figure out that you get quite a lot of different types of weather. It's not always the same. In London, the summers are short, comfortable, partly cloudy, and the winters are long, cold, and mostly cloudy. To be honest, I would say most of the year is probably cloudy at the moment. Now, over the course of the year, the temperature typically varies in London from about 4 degrees Celsius to 23 degrees Celsius, and it's rarely below -1 or above 29 degrees Celsius. So we've got a nice kind of like moderate temperature. We're quite lucky really to have. While there in London, you won't experience just that. You also experience wind, rain, snow, sun, hail, lightning, sudden downpours, drizzle, fog, storms, all manners of weather sort of all over the year. And why is this? Well, weather is created by a combination of sort of the planet's rotation, atmospheric heating from the sun, and the Earth's own heat from its core, making sort of temperature differences around the planet which produce pressure gradients, along which air rushes, which is like these jet streams, which can bring in cold or warm fronts, high pressure, low pressure systems, all sorts depending on how the planet is being affected by all these factors. As you can tell by weather predictions and apps that tell you what's going to happen, it's pretty complicated with lots of variants done by sort of supercomputers now. I believe they take all the information in of what's going on and a supercomputer calculates and kind of predicts what's going to happen. Even then it can't predict it, as we know. Like tomorrow it will say it's cloudy, I'll be like, right, I'm not going to go out and do astronomy, turns out to be clear. You're like, oh. But that's the weather, it's really complicated. So that's probably about as deep as I can go into it, because I'm not a meteorologist or anything like that. You standing on the Earth's crust, looking up at all the weather, the atmosphere and everything that's going on up there, all the stars and planets at night. But what's below you? Now we don't get to see this because unless you dig really deep, but we don't think we've dug that deep yet to actually get there. The crust bit that we live on is pretty thin. The mantle is beneath it, and it is a big part, about 84% of the Earth's volume. So the mantle underneath the little crust that we live on is 84% of the Earth and all its volume. So that's probably the big part. Now the mantle is a rocky shell about 1,800 miles thick. That's quite a lot. What was it up to space? 67, 62 miles? 1,800 miles thick. That's a lot of digging. But it allows hot material to sort of rise up through it, 'cause it's kind of porous or viscous, and it kind of rises up through it, pushing up, creating your volcano, keeping us afloat on top as the tectonic plates all kind of like move about up there. We then move on to the outer core. So this underneath the mantle, it's a liquid made up of iron and nickel at between 4,400 degrees Celsius and 6,100 degrees Celsius. So it averages around those sort of temperatures. And the movement of these liquid metals that are all under there is what creates our magnetic field. It's almost like a force field that protects us from the sun's rays. It's got all these loops of magnetic loops all going around. There's all this metal sort of spinning around, creating all this crazy magnetic stuff. Jupiter's is even worse, it's absolutely mad there. The inner core contains the heaviest elements because they've all kind of sunk to the core, as we said that when it's getting bombarded and stuff, all the gravity pulled the heavier elements down. And it has an iron-rich heart that is our planet. It has the same surface temperature as our sun, so inside the Earth is the same temperature as the surface of the sun, which is quite mad thinking about it. But it's solid due to the immense pressures pushing down on the core. Now the constant very slow movement of the planet's crust, mantle upon the outer core, is what creates our landscapes, mountains. Mountains are sort of thrusted up as tectonic plates smash against each other. Just like if two cars crash into each other, the bonnets are sort of pushed upwards. Or sometimes you have the opposite where one gives way and goes underneath the other. They go below, sometimes both go below. Sometimes they sort of slide opposite directions from each other. Sometimes they push against each other, and when they push against each other, sometimes they don't actually go up or down, they just keep on pushing until the pressure gets so immense that eventually one will give way one way or another and suddenly shifts, and that's what creates an earthquake. It's this sort of our tectonic plate shifting suddenly. I don't think they move that far, but when they do, think about it, it's that whole plate moving, and that's immense pressure. So we have earthquakes, unfortunately. Luckily in this country we don't get to feel them very often. I did feel one in Turkey once, and for someone, you know, it was a light one. Sat there sunbathing quite happily, reading a book probably on astronomy or space, and I noticed a sort of weird feeling like I was drunk. I was thinking, I haven't had that many yet. I looked at the water and it's kind of slowly vibrating in the pool. I thought that was weird. I just felt strange for a little bit, maybe about 10-20 seconds. And then my missus come running out. She said, "Did you feel the earthquake?" And I was like, "Ah, is that what it was?" So I felt one. It's quite cool, but obviously not if it's a big one and it takes down your house and things. Now all of this and more help shape our planet. The weather, the spin, the size, the tilt creates a sort of wonderful array of habitats or zones around Earth. They range from dry, dead, sandy deserts to frozen cold Arctics, lush, humid, thriving jungles full of life, wild plains of grass. You've got forests, woodlands, rivers, glaciers, tundra. Our planet's just full of diversity, wonder, and loads of things to see. Go out, look up at the skies, because I'm an astronomer, I have to say that. Enjoy the worlds around you and the stars, but don't forget the world that you're actually living on. We're flying around in this ball of rock around the sun. So go for a walk in a nice green lush park full of life. We may not see it as we do the other planets through a telescope, but ours is teeming with adventure to be found. So join the Parks Trust Nature Day. The website's here for you. You can learn more about our green spaces and the nature that lives alongside us. Now this is a little video that I found from the ISS as it kind of passes over the Earth. So I hope you enjoy it. Clear skies, and remember, there's a billion worlds in your back garden. Happy International Earth Day.
We are, by nature, explorers. the same curiosity that sends us to the stars at the speed of thought. Urges us to go there in reality. And whenever we make a great new leap, we elevate humanity, bring people and nations together, usher in new discoveries and new technologies. So remember to look up at the stars and not down at your feet. Be curious.